So now we will move forward to some more messy stuff about the pinch off. Now this is the question here, right? So I have a transistor. I decided to bias this at 2 volts and the drain at 0.5 volts. Okay. Now I want to ask how much electron I have along the channel. At this point, right, and let me assume the VTH equal to 1 volt, right? At this point, what is the charge that I have? That is mobile. Is the capacitance times the gate voltage minus the channel potential and then minus the threshold voltage, right? Which is C ox times 1. The point is that I want to say is I do have charge induced. Make sense? Right? Just remind you. Q, which is the electron density, equals to C ox times Vg minus Vx minus Vt. Right? That is what I'm using, this equation. I hope you're really familiar with this. It's not a difficult equation. If you understand, you're just talking about Q equal to CV. That's it. Terminal 1 minus terminal 2 times C ox equal to the charge. Right? How about at this point? This point, which is X equal to L, it has C ox times 2 minus what is the potential at this point? Vd, right? Which is 0.5 minus 0. No, minus 1. 1 is the threshold voltage. So this point, I have about 0.5 C ox. Right? This has 1 C ox, right? So I have less electron here. No surprise. We studied that last time, right? Remember? The channel potential keep increasing. And then look at this, right? This one. And then the charge keep reducing, right? When you go from the source to the drain. So nothing special. Now, but what if I decide to keep increasing the drain voltage? Now I increase it to 1 volt. What happened to the source? Well, source is still equal to C ox. Vg is 2. Vx is still 0. Vth is still 1. So this is still C ox. Nothing changed, right? Of course, this is a first order approximation. But here, if you look at the drawing, you see something is changed. Q equal to C ox times Vg, still 2. Vx is 1 because the Vd is 1 now, right? Vth is 1, right? You get no charge. We'll study that later. Is there any current flow? That's a very good question, right? But no charge at the end. So that's my question. We'll keep increasing, right? Eventually, when you see why it fell, when when happened, when Vg minus Vd minus Vth equals to 0, right? Because you need to recognize this. How do I get this 1? This is just Vd. Vg minus Vd, right? This is the potential at this point, which is Vd. When Vg minus Vd minus Vth equal to 0, then Q at X equal to L is 0. We call this pinch off. Okay? At that location, you don't have a lot of electron. We approximate it as 0. Is that okay? This is just the situation, right? So let's continue. and see what happens. Now, if I keep increasing the drain voltage, let's say to 1.5 volt, then the charge here is still Cox times 2 minus 0 minus 1, because Vg is 2, Vx at 0 is 0, right? At the source is 0. Threshold voltage is 1, so Cox. How about this point? If I still use this equation, Cox times 2 minus 1.5 minus 1, I will get negative 0.5 Cox. This is impossible. When I say I get negative charge, it basically is saying that I'm trying to induce the hole, maybe, right? It doesn't help, right? Because the equation breaks down. It's not applicable anymore. This is because now we actually don't have a constant depletion, right? Actually, they use this to sustain more depletion charge than the inversion charge. But we do not want to go into details. We just agreed that this will happen for this class. But that is what I mean by the equation breaks down, right? Equation not working anymore, because when I write this equation, I'm assuming that the depletion width does not change, and actually the local VTH change a lot, right? But don't ignore what I'm saying, right? The point is, I hope you to agree that this one will not work anymore. So we don't have charge. But however, think about that. We do have a point here at L1 that must satisfy the condition that at this point, Vx, what's going on? Sorry, some problem with the... It's recording, what? Okay. At this point, this Vx equals to 1 volt. Right? Look at this. This is 0, right? And this is 1.5, right? There must be a point that the potential equal to 1. Do you agree? Because I start from 0 and all the way to 1. The potential, there must be a point that is equal to 1. All the way to 1.5. There must be a point that is equal to 1.5, right? So this is L1. At this point, Vg minus Vx equal to L1 is just Vg minus 1 volt. And at this point, because it's 1 volt, Vg minus Vx equal to L1 minus Vth equals to 0, right? Because at this point, Vg is 1 volt, Vx is also 1 volt. I mean, Vg is 2 volt, I'm sorry. Vg is 2 volt. Vx is 1 volt and Vth is 1 volt. So you just pinch off. So what we say that it just pinch off. Okay. Now, then you might have many questions. It's not easy to understand and all very messy slide, right? But the thing I want you to have in your mind, I don't have animation, is that you start with a very low VD. You have a pretty uniform induction of the electron underneath. A lot of electron, like water, right? Along here. And it must be more on the source and less at the drain, because Vg minus Vx minus Vth is smaller at the drain, because near the drain we have a higher potential. If I keep increasing the drain voltage, there must be a point at which you induce no electron here. Okay? If you keep further increasing the voltage, this point will keep moving into the channel, right? Because the point at which you get no electron is when the channel potential is 1 volt in this case. So if you keep increasing the drain voltage, this point will keep moving into there. So you will pinch off earlier. Okay? Like, these are just some assumptions, based on some simplification, but this is a good picture. Some of you will think, wow, you say there's no electron, then does it mean that there will be no current? But it is not, because in reality, you still have some electron, very few. However, this electron is traveling at the highest speed it can attain. They are traveling at almost saturation velocity. What we call this saturation, which we did not discuss earlier for this graph. You see, it is under high electric field, it will travel at saturation velocity. And this is just like a waterfall. Think about this waterfall. You have water coming in. I only have a very gentle slope, and then I suddenly have a very large cliff, right? So here I have a lot of water because it is the river, right? It is the river. Oh, I don't know what's going on. It's just like the river, right? I have a lot of water. And then you suddenly travel really fast, you go down. And you can imagine the waterfall should have a less density compared to the river, right? So that you have the same amount of water going through that region in every unit of time. Imagine something like this. Okay? So the electron, I have a lot of electron here, they travel slowly. And then when I come to this cliff, they just, I don't have a lot of electron, but each of them just boom, boom, right? Very fast, just pass through this cliff to the drain. And this is called pinch off. So I want you to recognize first, we have pinch off. Second is this point keep moving into the channel when you increase the drain voltage. Okay? Then what happened? Why I want to say that? I'm not going to test you this in the exam, but I feel that you should understand this, right? So what do I want to say? Now we have one another region of operation. We never mentioned the cutoff region. We actually mentioned, but did not really emphasize this. When VGS is less than VTH, current equal to 0. This is the cutoff region. You agree with that, right? Your transistor is completely off. We also derive the equation when VGS larger than VTH. However, before the pinch off. When do we have the pinch off? Let's look at this again. When VGS minus VDS minus VTH equal to 0. If you rearrange them, right, you can go home to rearrange, but basically it is this. When VGS minus VTH larger than VDS. I say right. Smaller than VDS, I'm sorry. Yeah, smaller. Smaller than VDS. That is the trial region you just mentioned, right? We call it linear or trial, which is W on L, mu C ox, VGS minus VTH times VDS minus VDS squared divided by 2. Right? We derived this, kind of derived this, right? There was the region where you still have some electron at the drain before pinch off. This is important, right? Before pinch off.
Where is pinch off?
For the trial region, we don't have pinch off before.
Before the trial.
So as soon as we hit saturation.
No, I mean trial region means that it is before pinch off. That's what I mean. You start with this, right? No pinch off, right? So this is the trial region. When I keep increasing VDS, eventually you pinch off.
And so that's the opposite of saturation.
Yes, yes.
Yeah.
I mean, linear and trial is the opposite of saturation. Is that what you're asking?
Yeah.
Yeah, okay. So, but if we keep increasing the VDS, eventually you will have the pinch off. This is after pinch off occurs, right? And that is the case when, of course, you still need to turn it on with VGS larger than VTH. But now the VGS minus VTH is going to be larger than, I think I keep saying the wrong thing. Yeah, swap. Sorry. Everyone, I say the wrong thing, right? This should be larger than VDS. This should be smaller than VDS, right? I keep saying the wrong thing. Again, trial and linear is when VGS minus VTH larger than VDS, right? It means your VDS is still small, right? You're small, so you're linear. Now my VDS is large. How large? Larger than VGS minus VTH. Then you go to the saturation, and the equations becomes this. The most important thing is that it does not depend on VDS anymore. It's no longer a linear resistor or even a regular resistor. Okay? So if we look at this graph, where we plot ID versus VDS, 1/2 is here. Yeah. Oh, over here. Yes, 1/2. Very good. Yeah. Yeah, good. So when you have a small VDS, what happened? Like this, small VDS, right? I had just like a resistor. When I increase VD, ID increase. Eventually become nonlinear, but once you reach VGS minus VTH, it just saturates. Constant current. And we can understand a little bit by using this figure. The current basically depends on the profile of the electron, right? If I have a similar profile and I have the same potential across it, this is 1 volt, this is 0, this is 1 volt, this is 0. After pinch off, you keep moving it, but the other terminal is still 1 volt, right? It's just that when you go to this high electric field, you fall down very fast, but you will expect they should have the same current. So would you agree with that? Because just like I draw a resistor in this shape, it represents the concentration of electron. They have the same concentration. And then I have 0 at the left and 1 on the right of this triangle, right? Because pinch off, I keep going it pinch off at a point that is 1 volt in this case. So I should have the same current. Make sense? Any problem for what I'm saying, however?
So the slant line, that's just density. It's not representative of channel.
You mean this 9?
Yeah.
Yeah, you can say just where I have the electron. Yeah. Channel is still here up to here. Yeah. This is the channel. Channel is the electron, right? The inverted electron is the channel. Do I answer your question or no?
So what's producing the current limitation? Is it the width of the channel at the end?
Okay. So what is making them the same current, right? That you were asking, right?
Yeah.
Now, let's think about this triangle, just like this water flow, right? This river, right? I have 0 potential here and 1 here, right? Both has 1, right? Both have 1, right? So you have the same triangle, you have the same potential. Would you get the same current? I give you this amount of water here, and then you just tune it so the left and right has the same potential difference. You should get the same amount of current flow, water current flow, right? But do you completely agree what I say? They will be identical? Yeah, approximately they are, but everyone agreed that I claim that they have similar shape, same left and same right potential, and then they have the same current, right? But anything I'm approximating is what I'm saying 100% correct? What is not really 100% correct? Very good. Then this triangle, they are not exactly the same. I just think that they looks like the same, right? But now actually the length of this triangle, they are not the same. This one is shorter. Okay? So here I claim that they are the same, right? So you have the same saturation current. Okay. I will go to that part later. So this one we already mentioned, so I won't spend time. But basically, you see that this is the linear region. And particularly at this region, you can operate it as a resistor. Right? This part is the saturation region. I is constant. Do you see that? Regardless of VDS, right? You apply this VDS, I get this current. You apply this VDS, right? For example, this is 2 volt. This is 5 volt. I guess it's the same current. What type of components will give you this behavior? You apply 2 volt, you give you the same current. Apply 5 volt, give you the same current. What do we call this component?
Ideal current source.
Ideal current source. It's a current source, right? So whatever you give me, I give you a constant current. So this is very important in this class. We are going to operate in the saturation in many cases. Okay, but I hope you understand. By changing the VDS, I can make a transistor like a resistor, or I can use it as a current source. Okay, and why it is a current source? Because when you keep increasing your VD, the pinch off will keep moving in, and so